Okay, in this unit we're going to be studying things that rotate. And just like in studying just linear motion, we started out with kinematics. We're going to start out with kinematics for this as well. So rotational kinematics. And the first thing we're going to do is we're going to just reinforce something you already know, and that is the radian. That's the angle that we're not going to use degrees as much as we're going to use radians for angles in here. So if that's a circular object, if you have a circle, rather, and it's got a radius r, and if you start at the edge of that circle, and if you walk one radius around the circle, so that would be like right about there maybe, would you say that distance is equal to this distance? Because if it is, if this distance and this distance are equal, then you've just walked through 1 radian of angle. So that's what a radian is. So if this thing is spinning around, if it goes through 1 radius every second, then we say that it's going at a rate, it's spinning at a rate of 1 radian per second. Let me show you that. Here's a circle, and I'm gonna get it going, and this is spinning at 1 radian per second. There you have it. I don't know if you can see the time over here, but the time is actually it's taking about 6.28 seconds to go around every time. It's already gone around 3 times, and it's a little over 18 seconds. It's going around a 4th time, and we're at about 25 seconds. Okay, so that's 1 radian per second of angular speed. Well, it turns out then that we're going to tell you then that angular speed, we're going to have that's going to be, we can't use v for velocity or angular velocity. We're going to use some Greek letters. So this is a Greek letter omega. It is a vector quantity. It's angular speed, or angular velocity rather. If it's a vector quantity, it's angular velocity. There's theta, which is an angular position. And there'll be delta theta, which is an angular displacement. Okay, the angular position is measured in radians. So is the angular displacement. And the angular velocity is going to be measured in radians per second. And you can count on a few things. Angular velocity is equal to not delta x over delta t, but delta theta, the angular displacement, over delta t. The instantaneous angular speed will equal d theta dt. That's just like v is equal to delta x over delta t. But v instantaneous, this is average. But v instantaneous is dx dt. Same idea. Okay. Now there's also, as you probably are going to guess, there's angular displacement, or there's angular acceleration as well. So an object can be rotating with a constant angular velocity, but it can also have an angular acceleration. Let me show you. So here we're back to our circle. I'm going to do something to give this a little bit of an angular acceleration. All right. And I'm going to start it from rest. This time it's going to start from rest and have an angular acceleration. So here we go. So it starts out slow. And you see it is moving, but it's just moving with very low angular speed. But this is actually gaining speed. So every second it's going to be getting faster and faster. When I first started it, it almost didn't look like it was moving at all. But then right now it's going at a fairly good clip. But by the time it makes one rotation, it's going to be moving much faster than it did at the very beginning. This has, we say this has an angular acceleration then. I'll let you see this for maybe one more turn. And you'll see that it's getting faster and faster and faster and faster and faster. Its angular velocity is going up, 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 up. Now, what's nice about this is that everything that you've already learned about acceleration is contained in angular acceleration, except we can't use an A for angular acceleration. We use an alpha. So alpha is going to be angular acceleration. It is a vector quantity. I'll tell you about its vector nature in another video. Angular acceleration is average. The average angular acceleration is delta omega over delta t, just like A average was delta v over delta t. Let me get all these vectors in here. Boom, boom, boom. Well, instantaneous acceleration, angular acceleration, is d omega over dt. Just like A instantaneous was dv over dt. It was the derivative of v with respect to time. This is the derivative of omega with respect to time. Okay, well, here's the deal then. All those equations that you've memorized, hopefully, for your quick drill, namely V final is equal to V initial plus AT. Well, there's a counterpart in rotation. It's omega final equals omega initial plus alpha t. Isn't that nice? So these two go together. This is for rotation. That's for linear motion. How about V final equals V initial plus V final squared equals V initial squared plus 2a delta x. Well, that counterpart to that is omega final squared equals omega initial squared plus 2 alpha delta, not x, but theta. And then finally, you know how delta x, these guys go together. Delta x in linear motion was vi times t plus 1/2 at squared. Well, in rotational motion, delta theta is equal to omega initial times t plus 1/2 alpha t squared. So these are the kinematics equations. Now you can only use these, this one, and this one. These you can only use for constant alpha, just like the other ones. Okay, well, this is going to actually take me another video to talk about, so I'll see you in a bit.